So we're back online. So the first question is, which is more energetic, so holds the most energy? Yellow light that has a wavelength of 580 nanometers, or blue light that has a wavelength of 470 nanometers? So is it the yellow? Are they equally energetic, or is it the blue light that holds the most energy? Note your answer. We'll go through all of them, and then we'll go through the answers, because that's how I put it here. But you're, of course, right, everybody. So, okay. Through which physical process does infrared radiation interact with matter? So absorption. Is it through changes in rotational energy, changes in vibrational energy, or through this electron excitation, de-excitation? Make a note. So infrared radiation. Yeah. Move on. We'll go through everybody, and it's just like four questions, I think. Okay. Question 3. Consider two perfect black bodies. One is heated to a temperature of 300 Kelvin, and the other to a temperature of 600 Kelvin. How much more energy does the warmer black body radiate? Is it twice as much, 8 times as much, or 16 times as much? And here's the more tricky one, okay? Consider two planets that are identical. They have the same size, the same distance from the sun, they receive the same amount of sunlight, etc. The only difference is that planet A has an emissivity for all wavelengths of 0.9, and planet B has an emissivity of 0.3. Which one will be hotter? Will planet A be hotter? That has the higher emissivity, so closer to being a black body. Will they be equally hot, or will planet B be hotter? That one's trickier. Okay, so here are the answers. Which is more energetic? And you all shouted blue, or all, but the ones of you who shouted blue. So yeah, the higher the frequency, the shorter the wavelength, the more energy the radiation holds, right? So energy is, you can hear this is actually this Planck's constant times the frequency, or it's divided by the wavelength. So anyway, the shorter wavelength, the higher energy. Okay. Infrared radiation interacts with matter through changes in vibrational energy. Microwave was through rotation, and then for this excitation of the electron to occur, you must have much higher energy intensity of the radiation, so visible and shorter wavelengths. How much more energy does the black body radiate if you double the temperature? Well, the intensity of the radiation is governed by Stefan-Boltzmann's law, which is intensity equals the emissivity times the Stefan-Boltzmann's constants times the temperature to the power to 4. So if you double the temperature, well, intensity goes up by 2 to the power to 4, which is 16 times as much. So the increase is very fast with it. And the planets will be equally hot. And the reason for that, I'm going to actually do this on the board in a minute, is this Kirchhoff's law. The emissivity equals absorptivity. So planet A will absorb a larger share of the incoming solar radiation, but it will also emit more radiation. So in the end, they will have the same temperature. But we're going to do this on the board, and you can see and see if you. What did you guess? How many thought that planet A was hotter? How many thought that planet B was hotter? A few. Yeah. So it's it's not easy to have an intuition for things that you just started learning. So this was a tricky one. So what I'm going to do now, I'm going to put up a very simple model of the greenhouse effect, and we'll see actually how far we get with this. And then we're going to continue working on the same type of model tomorrow as well. And that's the focus of the two first calculation exercises you got. And it's also in the book you have this type of calculations. So the first question is, if we think about the Earth and think about a state where we didn't have an atmosphere at all, what would the temperature of the Earth be then? And that we can calculate very easily, but quite easily with this Kirchhoff, or with what we learned so far. I wonder if, no. So think about, this is the surface of the Earth. We have solar radiation coming in. We'll denote that by I. I can say IS even, where it's solar radiation that comes in. Some of that will be reflected directly back into space from ice and snow and so, let's say. So we'll say that alpha times IS will be reflected back into space. So that will not sort of interact, will not heat the Earth at all. It will just be reflected back. And then Earth, because it has a temperature above 0 Kelvin, will emit radiation. We'll call that F out. Okay? So the first exercise you have in the calculation exercise is actually just based on the temperature of the surface of the sun and some other data. You can actually calculate this. How much energy from the sun reaches the Earth's surface. But here we'll just say that. So that IS is roughly 340 watts per square meter. And then alpha is roughly equal 0.33. So a third of the incoming solar radiation is just reflected back into space. Okay. And then we have a temperature of the surface here. So what is the temperature here? Well, we can figure that out by assuming one central thing here, and that is what we call energy balance. So if there's energy balance, if the amount of energy that the Earth receives, takes up, absorbs, is equal to the amount of energy that is radiated back into space, then the temperature doesn't change, right? So if we have a constant temperature, then the amount of energy absorbed must equal the amount of energy that's radiated back. If more energy is absorbed than is radiated back, then the temperature will go up, right? If more is radiated out back into space than is absorbed, then the temperature must be decreasing. So we'll always reach sort of an equilibrium where you have this energy balance. So if we have energy balance, then the amount of energy that comes in. So this is the 1 minus alpha times the intensity of the solar radiation, right? That's the amount of energy from the sun that is absorbed by the Earth's surface. Must equal F out, right? And how can we express F out? Shall we try with Stefan-Boltzman's law?
Yes.
Huh? Good. So emissivity times sigma times T to the power 2 4. Right? Which means that temperature of the Earth must equal fourth square root of 1 minus alpha is divided by epsilon times sigma. Right? So we have, if we put numbers in this, we have 1 minus 0.33 times 340. And this is in watts per square meter. And then we said that we can treat planets like Earth like close to a perfect black body. So epsilon here is 1. And sigma was Stefan-Boltzmann's constant, which was 5.76 times 10 to the power to minus 8 watts per square meter and Kelvin power to 4. Okay, and we can look at the units here. We have watts per square meter. This is unitless, this is unitless. Watts per square meter divided by watts per square meters per Kelvin to the power to 4. And then we have the 4 square root here. So what we get is something in Kelvin. Yeah. This is roughly equal to 251.8 Kelvin, which is roughly equal to minus 21.4 degrees Celsius. Do you think this is the average temperature of Earth? Minus 21 degrees Celsius?
No.
No.
It's too cool.
It's so cool, yeah. And the reason it's not this cold is because we have the natural greenhouse effect. Okay? So, and of course, I mean, if we didn't have natural greenhouse effect, actually the temperature would probably have been even colder, because now we have assumed this the alpha here, 1/3 of the incoming solar radiation going back into space. That is actually how it is today. Of course, if the average temperature would have been minus 20 degrees, then we would have had much more snow and ice, which would have meant that even more of this radiation would just have been reflected back into space. So if that had been higher, then temperature would have been even lower. We put up this exact same expression for, you remember our two planets, planet A and planet B. So for planet A, we had the emissivity was 0.9. So 0.9 of the incoming radiation was absorbed. And then what is emitted is also 0.9 emissivity times sigma times T A to the power of 4, right? And planet B, 0.3 times the incoming radiation equals 0.3 sigma TB over 4. Are you okay with that? So this is just the energy balance for our simple planets here. What differs here is just they are not perfect black bodies. So they have an emissivity or absorptivity of 0.9 or 0.3. While you see that these just cancel out, right? So the temperature will be the same. If the incoming radiation is the same, they will be the same. Yes, it's a good question. So this didn't look exactly the same here, right? Why didn't it? So here we had here we actually, so I have the emissivity here for Earth, and I say that this is 1. It's a black body, right? But then I say it's not 1. So it's a perfect black body here in terms of emitting radiation, but it's not here. It doesn't absorb all the incoming radiation. So does not Kirchhoff's law hold here? Why is there a difference? Any ideas? So if we go back to Kirchhoff's law, what does it say, really? It says that if an object can absorb in a given wavelength, it can also emit in that wavelength, right? Mm-hmm. So Kirchhoff's law holds for sort of a given wavelength or a given area of the spectrum. But different objects can have a different emissivity or absorptivity in different parts of the spectrum. So like for hydrogen, you saw, I mean, it had high absorptivity, emissivity in specific regions, or in like certain wavelength, and then it was 0 for the others. So this is, so for Earth, in the visible spectrum, it's not a perfect black body. A third of the radiation is just reflected back into space, and it's not absorbed. But in the infrared spectrum, where Earth radiates, there we can treat it as a perfect black body. Does that make sense? You're So what it said is in the infrared spectrum, because of the temperature of the Earth it's much lower than the sun, right? So where the Earth primarily emits radiation is in the infrared spectrum. And there we can treat it as a perfect black body.
Only
in the infrared spectrum, yeah.
As you only this.
Yeah.
Perfect black body.
Yeah. But not necessarily in other parts of the spectrum. So that's why the absorptivity for the visible radiation is not the same as the emissivity of the infrared radiation. The main point here, the key to remember is this. Kirchhoff's law is sort of say that an object will be equally good at absorbing and emitting radiation at a given part of the spectrum. But it can be different in different parts of the spectrum. So what determines why it's good or bad? Yeah. So that we'll look a bit into it more tomorrow. But when it comes to the infrared radiation, it turns out that, well, for all the infrared radiation, Earth isn't really a perfect black body, but the atmosphere is good at absorbing in certain parts of the infrared spectrum, but in other parts it's not very good. And that depends on which molecules you have in the atmosphere. So it depends again on this, which sort of degrees or levels of infrared energy that the different molecules are able to absorb or emit. So you will have different gases. So water vapor will be good at absorbing infrared radiation in some areas of the spectrum, but not so much in other parts. And then you will have carbon dioxide, which will emit and absorb radiation in some parts of the spectrum. And you'll have methane in other parts. And partly these are overlapping. And then you have some areas of the spectrum where there are actually not many gases that are so good at absorbing and emitting infrared radiation. And that radiation goes out into space. So if you then introduce gases that are very good at absorbing infrared radiation in this area, where not gases are absorbing today, they are very strong greenhouse gases. But we'll talk more about that tomorrow. But it's good. That's where we're getting at. So let's make things a bit more complicated. Can I erase this? And this basic model you have in your. Okay, so let's make things a little bit more realistic. Let's add a layer here, an atmosphere, that doesn't affect the visible radiation here from the sun. So it just moves through like our atmosphere. Most of the radiation just goes through, and some of it is reflected back. But so now we have outgoing radiation here, infrared radiation from Earth. Let's call this F surface, like Fs. That will be completely absorbed by the atmosphere. So let's assume we have an atmosphere that absorbs all of this. This is just one layer. So in your textbook, which you have a PDF now, I think hopefully most of you in the inbox, the model we just did, where we got the minus 21 degrees temperature of Earth, David Archer called us the bare rock model of the Earth. And this is, he calls the layer model, or one layer model. So we have simplified things, so the atmosphere is just a single layer here that absorbs all of the outgoing infrared radiation. And because this also has a temperature then, the atmosphere here, that will radiate out energy as well. So it will radiate energy back to Earth. And what did I call this? Let's call it C back, so back radiation. But it will also radiate infrared radiation out into space. Let's call this F atom. Okay. So let's now try to solve this for the temperature of the Earth. And then again, we can put up the energy balances here. So if we put up the energy balance for the surface, so what's the energy that is absorbed by the surface here? As before, we have 1 minus alpha I sun. Is there any more energy that is absorbed by the surface? F back. Exactly. Oh, sorry. Plus F back, and let's do it so it's clear. F back. And what leaves the surface? Speak up. Oh, yeah, that what we already sort of accounted for there, but that's true. We could have put just IS here, and then we could put alpha IS here, but now we just put it all here to get, from the start. But so what is left is this, some of you said FS, right? So we just rewrite this, so we have 1 minus alpha IS plus, how do we express F back? Yeah, we can rearrange, but if we want to relate this through sort of temperature, if we want to use Stefan-Boltzman's law here, what determines the size of F back? Emissivity of the atmosphere, right? Times sigma times the temperature of the atmosphere, part 4. And this equals the emissivity of the surface times sigma times T of the Earth. Call this for part 4, right? And then we can also put up the energy balance for the atmosphere layer. So what is the incoming energy to the atmosphere?
Yes.
Say again?
IS.
No, this radiation just passes through the atmosphere, right? Fs, yeah. So we have Fs that warms the atmosphere, and then what does it radiate out back again? F at plus F back, right? So should I write this? So if we use Stefan-Boltzmann's law again to express this, we have Fs is epsilon the surface times sigma times T of the surface power to 4. Can you see when I write down here? Should I move up? It's fine. F atmosphere, that's epsilon of the atmosphere times sigma times T of the atmosphere power to 4. Now you're bending your neck, so I'm going to move up there soon. And what is F back? Well, that's just the same, right? E at times sigma times T at power to 4. Sorry, good, yeah, plus. So because both this F back, the radiation that is radiated back to Earth and the radiation that goes out to space is determined by the temperature of this layer. It will be the same. Right? So if we assume here that these are all, both the surface and the atmospheric layer here are perfect black bodies for infrared radiation. Yeah, sorry. Exactly, so now I wrote it as, yeah, just plus plus, but you can write it as 2 times, yeah. Yeah, so this is, the right-hand side here is 2 times epsilon at times sigma times T of the atmosphere to the power to 4. So if we assume that the emissivity of both the surface layer and the atmosphere is 1, they are perfect black bodies when it comes to infrared radiation, well, then we can rewrite this and say that the temperature of the atmosphere, power to 2, power to 4, must equal temperature of Earth, power to 4, divided by 2. We find that? Fine with that? It's just simplifying what stands here. So here we have, so we assume that this is 1 epsilon. So sigma times the power of Earth, temperature of Earth, the power to 4, equals 2 times sigma temperature of the atmosphere, the power to 4. Yeah? Oh, yeah, but this is sort of, so in reality, of course, you will have radiation going up and then being absorbed here and re-emitted, warming the surface, going back up, da 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 da. So this is just sort of the net effect. But you're right, of course, there is constantly radiation going back and forth here. Yeah, that's a good point. So in reality, and you'll see this when I draw it in the calculation exercise, you will have sort of, some of it actually bounces off sort of clouds here. And some of it goes all the way down and reflects from snow and ice at the surface. But the sigma here is sort of the net of these two. But that's a good point. Yeah. What we can do now is we can plug into, so now we have, because in this, the energy balance for the surface we have both the temperature of the atmosphere and the temperature of the Earth. And if we want to figure out the temperature of the Earth, well, if we plug in this, we know that the temperature of the atmosphere, the power to 4, equals temperature of the Earth, the power to 4 divided by 2. Then we can actually solve this, because we know alpha, we know IS, we say this is 1, and so on. So then we can write again the energy balance for the surface. You can rewrite this. So we have 1 minus alpha IS plus, let's skip the epsilon. So we have sigma T Earth power to 4 divided by 2. So I just replace the temperature of the atmosphere here with temperature of the Earth divided by 2. And this equals sigma T Earth power to 4. And I'll write this up and then I'll go through it. So we solve this for the temperature of the Earth. So if we move this to the other side, so here we have sigma times T Earth to the power to 4. Move this to the other side, what we'll have left here is, so this is half sigma T Earth to the power to 4. So we'll have half. We'll have that this I minus alpha IS equals sigma T Earth power to 4 divided by 2. So we solve this for T Earth, and we have an expression that's very similar to what we had before. 4th square root of 1 minus alpha IS divided by sigma divided by 2. We put numbers again. 1 minus 0.33 times 340 watts per square meters divided by 5.67 times 10 power to minus 8 watts per square meters per Kelvin power to 4, and then divided by 2. And now we get 299.4 Kelvin, which equals 26.2 degrees Celsius. So instead of having an average temperature of the surface of minus 21 degrees, we have a average temperature of plus 26 degrees instead, which sounds much more comfortable, right? Yeah. This is, and we'll get into this, because one thing we assume now is that this atmospheric layer is perfect. It absorbs all of the outgoing radiation here. So what you're going to do in the calculation exercise is we change this slightly and allow some of that radiation to go directly out to space, and not all being absorbed, which is more closer to reality. And then you can see what actually happens with the temperature there. Let's look at this then. So we know that the temperature of the atmosphere. What's the temperature of the atmosphere here? Well, it's that temperature power to 4 divided by 2. So T at will equal T Earth divided by the 4th square root of 2. And if we put in this temperature here, for temperature of Earth, we get 251.8 Kelvin equals minus 21.4 degrees Celsius. Is that number familiar? Same as the temperature we got for the surface in the first part, right? Is that a coincidence, you think? It's like, I mean, could it have been different? If the Earth still receives the same amount of radiation from the sun, right? It still absorbs the same amount of radiation. So how much, it must still emit the same amount of radiation, right? And if we know the intensity, how much is emitted, and it's a perfect black body, then the temperature must be the same as well. So this, you can say, in a sense, is the temperature of the Earth if you look at it from space. If you're at a distant star and looks at the Earth and try to measure the temperature of Earth just by looking at the radiation that comes from Earth, well, you would think that the average temperature is minus 21 degrees. Because that's what you see from space. But thanks to this atmospheric layer here, we actually have a temperature at the surface that is much higher than that. So this is the greenhouse effect. So your task for tomorrow, we'll meet again tomorrow afternoon, and then we'll go through the first two calculation exercises. So they are not that dissimilar from this, so try to go do them. And you also have the same thing in the book, so you could look at there as well. And we'll look at both what the changes are when we allow some of this radiation to just continue straight into space, and also look at what determines the difference between the temperature here of the atmosphere and Earth. What are the determinants of that? What does that affect, or what determines it, I should say. So read the first couple of chapters in the book. The reading instructions are in the schedule. You have which chapters for today and for tomorrow. So read that and then have a shot at the calculation exercises as well, and we'll go through them tomorrow, the first two ones.